Okay, folks, now we're going to talk about geometric sequences, and we're going to refer back to the initial example I gave with the prize money. Option 2 turns out to be a geometric sequence. You can see it pretty obviously because the way the rules are set up, you start with $4, but in week 1 right here, okay, you've got $8 because you double it, all right, and then it goes to $16, okay, then the next one would be 32 in here, and then 64 in there, and then we just keep going and doubling that. And you should have come up with something here for a final amount, okay? And I want you to notice that in each case, we have this common ratio here that we're multiplying by each time, which is 2. Okay, so we're multiplying by 2 each time. So a geometric sequence, instead of adding something each iteration, we are multiplying by the same thing each iteration. So we call 2 the common ratio. We had the common difference for arithmetic sequences. Now we have something called the common ratio. Okay, so we're going to start off looking at geometric sequences by looking at the recursive definition or the recursive formula first. So let me pan to that quickly. Okay, so here's the recursive formula for a geometric sequence, okay? And the formula, I'm going to outline it in red right here, is right there, okay? So again, we define the first term first. For recursive, we always need to know the first term. And for geometric and arithmetic sequences. And then we base the next term off of the previous term. And that's what this means right here. Okay, again, an is the nth term in the sequence, and an minus 1 is the term right before that nth term. And I'm multiplying by a common ratio. Here's my common ratio, okay, which they also state right here. R is the common ratio, and n is the term number. And so they break it down really nicely over here too and explain it even further. This right here in purple is called the explicit formula. We're going to cover that in the next slide. Okay, so I can always build a sequence. Okay. I can always build a sequence using the recursive formula either for geometric or arithmetic sequences. And the way I build a sequence is I just give you a first term. So I say A1 equals, let's start with 10. And then I could say that my ratio is 1/2. Yes, my ratio doesn't have to be a whole number. It can be a fraction. It could be a decimal. It could be the number pi if I want my ratio to be pi. And so then my formula is that an is going to be 1/2 times I wrote an n minus 1. So to build my terms, I already know that a1 is 10. And then A2 is just going to be found by taking the previous element, which is 10, and multiplying it by 1/2, which would give me 5. And then A3 is going to be found by taking the previous element, which is 5, and multiplying it by 1/2, which is 5/2. And I could go on forever and ever and find as many terms as I wanted to. But that's how we use the recursive formula, and that's the official algebraic definition of recursive formula. So now we're going to go and look at the purple formula, which is called the explicit formula. So for the geometric sequence and the arithmetic sequence, we have 2 types of formula. One of them is the recursive formula, which is a formula that allows us to find any term on the basis of the term before it. There's also a formula called the explicit formula where I don't have to know the term before the first term, the term I'm looking at, in order to calculate the value of that term. So let's look at the explicit formula next. Okay, here is the explicit formula for a geometric sequence. It's in blue right here, okay? The explicit form says that if I want to find the nth term of the sequence, I take the first term and I multiply it by some power of the common ratio. They give a nice example here, 3, 6, 12, 24, where my first term is obviously 3. My ratio is 2. I'm doubling this every single time. And so my general formula, plugging in now 3, plugging in 3 for A1, okay, and plugging in 2 for my common ratio, I can actually develop a general formula for the equation. A general formula for the equation. And this actually makes a lot of sense that this is a power of 2. And the reason it makes sense is because I'm just basically figuring out how many 2's I have to multiply by to get from 3 to say, well, let me do a different color there, from 3 to say 24. So 24, if you notice, is A4. So the way I get that is I take A4, would be using the formula 3 times 2, and then since n is 4, it'd be the 4 minus 1 power. So this is 3 times 2 to the third, which actually makes a lot of sense because if you notice, I am multiplying 3 by 3 different 2's. That's why it's 2 to the third. Also notice the correlation here, that when this is a 4, this is 1 less than it. Just like when this is an n, this is an n minus 1. So that's a pattern that you see in there. That was similar to with the arithmetic explicit formula as well. It was for the arithmetic, just as a reminder, that equation was an. So that equals A1 plus n minus 1 times d. So you see that correlation happening in both of these, meaning, this is an n, this is an n minus 1, and then that's exactly the same as up above here, where this is an n and this is an n minus 1. Okay, so that's the general form of an explicit formula for a geometric sequence. Now we're going to run through an example that's kind of maybe out of the box a little bit. We're going to look at a geometric sequence that would kind of occur in an actual application in real life. Okay, let's take a look at this one. You deposit $5,000 into a savings account that bears 5% interest compounded annually. If you don't ever withdraw any money or spend it, how much will be in the savings account after 8 years? This doesn't seem like a compound interest a geometric sequence problem, but it is actually, and here's why. Because we start out with you deposit $5,000 into a savings account, so we start off with $5,000. Okay, and then what's going to happen is that since it's 5% interest compounded annually, the value of the balance in the savings account is going to increase by 5% each year. Okay, so this is going to be a 5% increase each year. Okay, that's going to mean that my multiplier is going to be 1.05 is my common ratio. Okay, that's just some percent increase review. When I have a 5% increase in something, I basically take the original amount and multiply it by 1.05. If I had a 10% increase, I'd multiply it by 1.10. If I had a 3% increase, I'd multiply it by 1.03. If I had a 20% increase, I'd multiply it by 1.20. So that's my common ratio. So what that enables me to do now is I take that 5,000 and I'm going to multiply that by 1.05. Pulling out my calculator, 5,000 times 1.05 is 5250. Okay, and then I could multiply that by 1.05 again. And I get 55 12, 50. Okay, so what I should notice is a pattern is this is, if I were to do off to the side here, this is year one. Whoops, my bad. This is after year one. This is after year two. Okay? And then I could just keep doing this recursively based upon the previous entry, and I could just keep going. So I multiply by 1.05 again, and I get 57.88 and 13 cents, and I could keep going. I'm actually not going to do each of these. I'm just going to jump to the end. I'd have to do it 5 more times because this is year 3, right? So I'm just going to go ahead and do that. So if I do a dot, dot, dot and do this on my calculator 5 more times, I get 73.87 and 28 cents. And that should be after 8 years. Okay? So this is my final answer. And that is a geometric sequence. And in this case, my A1, my first element or term in the sequence is $5,000. And my common ratio is 1.05. So that's a tangible example. So now you're going to get to work on an example in the flow of the lesson.